This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs. Also, make sure to check out and subscribe to our YouTube original channel, UCTV Prime, available only on YouTube.
We all strive to live a long, prosperous, and healthy life. With advances in health and medical sciences, this goal is ever more attainable. The Sam and Rose Stein Institute for Research on Aging is a nonprofit organized research unit under the auspices of the University of California at San Diego, committed to advancing lifelong health and independence through research, education, and patient care. To better empower and improve the lives of young and old alike, the Stein Institute presents the following program.
Hi, good afternoon. I am Dilip Jeste. I am the director of the Sam and Rose Stein Institute for Research on Aging here at UCSD, and welcome to this public lecture. I am going to take a few minutes to talk about the Stein Institute, and then I will introduce the speaker. As many of you know, the Stein Institute is the oldest institute on aging in the entire University of California campus. It was established in 1983 by Dr. J. Siegmiller. For the last several years, the focus of the institute has been on successful aging, especially successful aging of brain and mind. We have 135 faculty members from different departments, disciplines, and even schools who are interested in aging. We have a number of federal and other grants in various areas related to aging, multiple publications, and we are also very interested in research training. This training goes on at various levels, from faculty to fellows to residents to medical schools and even high school. We have been, for the last 5-6 years, running a training program for underrepresented ethnic minorities from high schools, such as the Preuss School here at UCSD. A couple of years ago, my colleague Colin Depp and I, we published a book called Successful Cognitive and Emotional Aging. These are chapters by different people at UCSD as well as rest of the country and even international. One important function of the Stein Institute is community outreach. This free lecture is a part of the free public lecture series that has been going on here for the last 25 years. These lectures are broadcast on UCSD TV, University of California TV, and YouTube, and they are seen all over the world. We also publish a monthly free newsletter called Successful Aging. The work of the researchers at Stein Institute has been widely cited in the media. While we have grants, we are dependent primarily on support from the community. I know that many of you have been generous donors, and we appreciate that. We have a website, aging.ucsd.edu, and if you have not seen it, I welcome you to visit it. And finally, it's my pleasure and privilege to introduce today's speaker, Dr. Larry Goldstein. Dr. Goldstein is a distinguished professor of cellular and molecular medicine and also of neurosciences here at UCSD. In addition, he's the investigator for the Howard Hughes Medical Institute. Dr. Goldstein is one of the most distinguished neuroscientists. He is a member of the American Academy of Arts and Sciences. His research focus has been on molecular mechanisms of movement systems inside the brain cells and how the pathology in the system leads to various degenerative diseases such as Alzheimer's, Huntington's, and amyotrophic lateral sclerosis. Dr. Goldstein is a major leader in national science policy. He was a co-chair of the Scientific Advisory Board for Prop 71, the Stem Cell Research Initiative, which led to $3 billion of California state bonds. And that's really an incredible initiative that helped undertake stem cell research within our state. Dr. Goldstein is also co-founder and consultant of a biotech named Cytokinetics. And recently he published a book called Stem Cells for Dummies, which has been very well reviewed. So it's really a pleasure and a privilege to welcome the speaker, Dr. Goldstein.
So, thank you all for coming tonight. It is one of the most beautiful evenings of the summer outside, and so I'm very impressed by you taking time out of your glorious summer evenings when the tomatoes are ripe and the barbecues are warm to come and join me to talk about, of all things, stem cells. So what I'll do in the time we have is spend a bit of time at the beginning talking about stem cells. What are they? Who are they? What little secrets are they hiding? And then how might one use them in theory to make progress in problems of human disease? I'll then give you a couple of specific examples where in my lab we're using stem cells to try to fight two really awful diseases, ALS or amyotrophic lateral sclerosis and Alzheimer's disease. And then I'll close by discussing a couple of the policy issues surrounding the application of stem cells to human medicine, in particular the issues with the first applications in humans of novel technologies and those who would take advantage of people who don't understand the various issues, the so-called snake oil problem. Okay, so let's really begin with basic principles and remind all of you that cells are ultimately the functional unit of the human body. They're the basic building block. And a very useful analogy I've found is to think about all of the different kinds of cells in your body as being like different kinds of small businesses. And what I mean by that analogy is that when we say that cells have different jobs, we're effectively saying that each of them is specialized or differentiated to do something special or have a special product. So pancreatic cells, their special product is insulin. You can think of neurons, their special service is to transmit signals, and heart cells, their special service, of course, is to contract, to pump blood. And so in that sense, all of these different types of cells are specialized or differentiated, and they are like small businesses in that way. Now, the reason that's ultimately relevant to thinking about human disease is that most, if not all of the diseases that we currently deal with in our clinics are diseases where you can think about the breakdowns as being at the level of cells, and in some cases, highly specialized cells. And that happens in two different ways. In some cases, cells are still alive, but they're damaged. And of course, the easiest example of that is cancer, where not only are the cells still alive, they won't die even when you want them to. That's part of the problem. And they get into places they shouldn't go, and they create mischief when they metastasize. So they're alive but damaged. Heart failure is another example of that, where the cells that contract to pump blood in the heart are still there. They're still alive, but they're damaged. They've gone through degenerative changes. The other kind of example are examples where cells have actually died and are gone. And type 1 diabetes, sometimes called juvenile diabetes, is a good example of that, where the beta cells of the pancreas, whose job is to make insulin, as I just said, those cells have died and are gone. And so they can't do their job anymore. They're just not there. Parkinson's disease is another kind of example like that, where special cells in a region of the brain that control movement have died and are gone, and that leads to the characteristic symptoms. Okay, so that's the bad news about disease. And so the question then is, what is a stem cell and why do we care? So let's start with the what is a stem cell part. So when all of you folks took high school biology, you learned something really important about cells. hopefully you learned many important things about cells. But one of the things you learned is that the way cells grow effectively is to divide to make more cells. And you learned that when one cell divides to make two daughter cells, those daughters have a particular relationship to each other. And I'm going to test you and see if you remember what that relationship is. What did your high school biology teacher tell you about those two daughters? They're identical, right? That's what you learned in high school biology. Those two daughter cells are identical. It's what I sometimes refer to as the biggest lie in biology. And the reason for that is it is true that the DNA of those two daughter cells is identical. But in fact, those two daughter cells ultimately need not be identical in their behavior. They can actually, in some cases, go on to do different things. And if you think about it for a moment, that's a really important property, because if you look at whatever person is sitting next to you, you'll notice that they're not just a pile of big pink dots. They're not just a pile of identical cells whose behavior is all the same, right? We've just said that they have all these different kinds of specialized cells. So in some way, there has to be a way for different cells to do different things. And stem cells are an example that account for much of that different behavior that you see when you look at an adult human or an adult organism. And so stem cells are cells that when they divide, even though the DNA content of those two daughter cells is the same, they can go on to do different things. And in this case, one of those cells remains a stem cell. So it's a self-replenishing pool of cells. And the other cell can go off to do one of the specialized jobs that we just talked about. So a stem cell can give rise to more stem cells and also to specialized cells such as neurons or pancreatic cells or what have you. So that's a simple definition for a stem cell. And the reason they're promising is you can think of them as being, in a sense, biological raw material to do things with that have biological or medical value. So I always like to go back to a very famous movie. You probably remember in the 60s there was a movie that starred Dustin Hoffman about Dustin Hoffman being seduced by an older woman. But there was a very famous line in that movie where a fellow named Mr. McGuire was giving Dustin Hoffman's character some advice about what he should do with his life. Plastics, there we go. All right, good. You guys are paying attention after all, right? There were other quotes of that movie that I will not repeat here. But the important advice was that Dustin Hoffman should devote his life to plastics. And that was great advice in the 60s, because if you fast forward to current times, we see all sorts of things that used to be made out of metal are now made out of plastics. My iPhone case, pieces of automobiles, pieces of airplanes. It's actually remarkable what you can build out of plastics. It's an incredible material. And if you fast forward, though, to the year 2012, this year, the advice that Dustin Hoffman would get would be stem cells. Because stem cells ultimately, in a sense, are biological plastics. And we are, in fact, at the dawn of an era of biological plastics where we're in the process of trying to learn how to take this biological material that can become any cell type in the adult and can also replenish itself. So we don't need to mine it. We can grow them in the lab. We have to feed them. They eat. But they'll grow to large quantities, and we are learning the biochemical signals to send those cells to tell them to become brain cell, pancreas cell, heart cell, what have you. And so you can see that in a very important sense, these cells may provide the raw material to replace cells that are damaged or lost to disease or injury. We'll come to examples of that in a bit. Or perhaps, as our bioengineers are beginning to do, to be the raw material to start building, for the moment, bits and pieces of organs. And ultimately, we hope, in the coming decades, it's not going to take a week, it's not going to take a month, it's going to take years, to learn how to build organs out of these biological materials that might be used for transplant. Now, that's clearly a very important potential use. But even more interesting, stem cells are not one-trick ponies, as we might say. In addition to being raw material for so-called replacement therapies, they're also turning out to be very important tools to understand and combat human disease and also as very important tools, again, just at the beginning now, to test and develop new drugs. So why is that important? So it turns out that if you look at the pharmaceutical industry and the biotech industry, something like 90% of all drugs that begin clinical trials fail. It's a remarkable number. 90% of what they do fail once they initiate clinical trials, which are really expensive, by the way. Now, you could ask the question, why is that? Now, one explanation is that guys like me are stupid and lazy. That's actually not my preferred explanation, it turns out. That's probably self-aggrandizing. And I think it really is not the correct explanation. A better explanation is if you actually look at the way we develop drugs. If you think about it, we cannot just take a random chemical out of my lab that we hope will make a person with a disease better and just start feeding it to people. We've got to do something to try to get evidence that a drug that we're going to test in people is likely to be safe and effective before we start pouring it into humans. And so we use animals, mice, rabbits, dogs, whatever. And in many cases, we use so-called animal models of disease. Now, the problem is that some animal models of disease are reasonably good. And some, as you'll see, are reasonably bad. And that makes some sense. If you look at, for example, a mouse, and you look then at me, you'll notice that I don't look like a big mouse. There are profound biological differences. First of all, I outweigh the thing by an enormous amount. Our brains are different sizes, our hearts are different sizes, our physiology is very different. And so the general principles of how the mouse works and how I work are similar within limits. But the details of what happens in the cells, the details of what goes wrong in disease, the details of how the mouse detoxifies and processes drugs are different than the way I do it. And so the ultimate outcome is that drugs that are safe and effective in a mouse are not necessarily safe and effective in a human. And so many drugs that go into clinical trials were safe and effective in animals or animal versions. That's good. I mean, that gives us enough confidence to try to test them in people. But the 9 out of 10 that fail often fail for reasons that they're not as safe in people as they were in animals, or they don't work as well for the disease as they did in animal versions of the disease. Well, okay, so what's that got to do with human stem cells? You could imagine that if I could make human versions of the various tissue types in a human in the lab, in dishes, I could begin to test those drugs on human cells and human tissues before I went into human clinical trials. And that then gives me a very powerful way, potentially, to eliminate drugs that might fail or to accelerate the development of those that might succeed if those models in the lab that we make from human stem cells turn out to be reliable. And in addition, those cells that have so-called disease in a dish give us very important tools to probe the details of what potentially goes wrong in human cells that have a disease. And it's a very important use, as you'll see when we come to a couple of examples. And so ultimately, at the end of the day, you can think of stem cell technology as being enabling technology. It's not one use. It's actually a set of tools that come with these biological materials that enable us to do all sorts of new things that will help us understand and treat human diseases that we can't currently treat effectively. Okay, so that's why they're useful. And so the question then is, where do you get them? You don't just go to Ralph's grocery store or the liquor store to buy them. They have to come from somewhere because they're a biological material. We don't dig them out of the ground. And there are really 3 major sources of human stem cells or stem cells from animals of a variety of types as of 2012. The first type that you've probably read a great deal about in the newspaper and the blogosphere are so-called adult stem cells. Now, I'll just tell you that the label adult stem cell is very misleading, not in a malicious sense. It's a very incomplete definition, as you'll see. And in fact, they're more properly referred to as tissue stem cells. And so let me tell you why. If you go home tonight, as I suspect you will, and look around, there will be household dust. And if you don't have a dog, as I do, most of that household dust comes from skin that the people who live in that house shed every day. A great deal of household dust comes from human skin that's shed. In fact, every day of your life, you shed enormous amounts of skin, and you'll realize something very important. If you shed old skin every day, new skin must be coming from somewhere. Because if you don't have new skin every day, you're going to have a problem. That's going to be a leaky mess. So where does that skin come from? It turns out that in the deep layers of the skin, there are stem cells whose job is every day of your life to replenish skin cells that you shed. And those stem cells stick around for most of your life. They replenish themselves, and then they also make new skin. And what's interesting about those cells is that they live in a tissue, the skin, which is why we might call them a tissue stem cell. And second, you'll notice that they're under very tight biological control in the following sense. A, they don't just divide whenever they feel like it. They divide in a very controlled way, so you don't have too much skin or too little skin, right? So they're very tightly controlled. And by the way, that makes biological sense. If you don't tightly control the growth and division of cells, that ultimately is cancer. The other thing you'll notice about those skin stem cells, and you can deduce this from first principles by looking at your own skin, is that their fate, their abilities are pretty tightly restricted as well. That is, every day those stem cells get up to do their job, and their job is to make skin. They do not begin to make brain cells, or eye cells, or liver cells, right? That's actually a very sensible biological restriction. You don't want your brain stem cells to wake up one morning and declare, I'm tired of making brain cells, today we're going to make liver. Okay? They're under tight control. And that's a general lesson about tissue stem cells, which are those we find in different adult tissues, and by the way, in different fetal tissues, which is why it's not accurate to call them all adult. It's a common mislabeling of these cells. Now, if you look in most adult organs and tissues have a stem cell pool. There are stem cells in the brain, we think in the liver, the intestine, perhaps in the heart, certainly in the muscle and skin and the intestine. And they are pretty tightly restricted in their ability to grow and to make different types of cells. Most of these cell types have been pretty elusive and hard to isolate and grow in the lab. There are a few that have been possible to grow in the lab. There's a kind of cell called an MSC, for mesenchymal stem cell, whose primary job is to make connective tissue like cartilage and muscle and bone. But then some very important cell types like stem cells in the bone marrow, whose job is to make new blood and new immune cells. Those are, even after 10 years of very hard work, almost impossible to grow in any quantity in the lab. Now, I'll just mention that among adult and tissue stem cells, there are two other kinds of stem cells that you may have heard of: cord blood and amniotic fluid. Cord blood is a type of tissue that has two or perhaps three different types of stem cells in it. There's a blood-forming stem cell, similar to what you find in bone marrow. There's a mesenchymal type cell that makes connective tissue, and there may be a kind of stem cell that makes blood vessels. A little unclear still at this point. But cord blood is not a source of cells that can make every adult cell type, as can the embryonic and reprogrammed cells that I'll come to in a moment. And amniotic fluid stem cells are probably the mesenchymal type, it turns out, although there have been those who would argue differently. I don't agree with them. Now, second type. Embryonic stem cells. These are the more ethically challenged in the toolbox of stem cells. These are stem cells that are extracted from frozen embryos that are left over after in vitro fertilization treatment for couples who can't have kids the old-fashioned way and who need technology to help them. As it turns out, in general, in a cycle of in vitro fertilization, more embryos are generated in the lab than will be used to start pregnancies at that time, and they will go into a freezer to be stored until a couple wants to try again using those frozen embryos to start pregnancies. Remarkably, human embryos can be stored for 10 years or more in a freezer and still be used to start pregnancies successfully. But like everything in your own freezers at home, they gradually lose viability or quality over time as they're stored. And of course, IVF, in vitro fertilization clinics, are private businesses. They sometimes go out of business. The bank sometimes ends up owning the freezers. Sometimes they just lose, the freezers die, break, what have you. And then sometimes couples actually wander off without paying their freezer bills anymore, and the clinics are, it's amazing, isn't it? And the clinics are left with the embryos, and they're unsure what to do with them. Now, it turns out that in many cases, probably more frequently than you imagine, couples who are done having kids, whether it's 1, 2, 3, or 4, will often have frozen embryos left over. And they are allowed by law, if they so choose, to donate those embryos to research instead of discarding them as biological waste. And there are scientists such as myself who believe that's an ethical and appropriate thing to do scientifically. And when those embryos are donated to research, they will be destroyed. But as part of that destruction, stem cells can be grown from those embryonic cells. And if you do this properly, under the right conditions, those embryonic cells will grow more or less indefinitely, as near as we can tell. They can be frozen and thawed over time courses of many years, and importantly, they have the ability to make every adult cell type, as near as we can tell. Now, can they make 100% of all adult cell types in the human? We're not certain. That's a hard experiment to really do and prove. But they appear to be able to make most, if not all, and a great deal of effort is currently being devoted to learning all the biochemical signals that tell these cells how to become all the different cell types that you might want to study or to generate for the treatment of disease. And it's a very active area of research in California and elsewhere. And you can see that these cells could be very powerful, potentially for treating disease, if we learn how to control them properly. And I'll give you an example of that in a moment. The final type of stem cell that's relevant to tonight's discussion is the so-called reprogrammed stem cell. So it turns out that as a result of work in the laboratory of a Japanese scientist named Shinya Yamanaka, a very cool genetic technology was developed that allows you to do the following. It's possible to take advantage of what we've learned about the behavior of embryonic stem cells so that we can take a skin cell from me, for example, and by introducing into that skin cell the elements of the genetic network that allow an embryonic stem cell to make all adult cell types and to grow indefinitely, we can convert that skin cell, we can reprogram that skin cell into a stem cell that has most, but not all, most of the properties of an embryonic stem cell. Now that's a very cool technology if you think about it, because A, it gives us another way to make stem cells that can grow to large quantity and make all adult cell types. And B, it allows me to make a stem cell line that has my unique DNA in it. So all of my unique patterns of genetic variation that make me susceptible to some diseases, resistant to other diseases, that allow me to be the charming fellow I am up here. All of those are captured in those stem cells in the lab and allow us to study, by making different specialized cell types, how the DNA reads out in the behavior of those cells and maybe gives rise to disease-related behaviors. It's a very cool technology, and I'll have a little bit to say about that momentarily. Okay, so it turns out that 12 years ago, I was testifying in a Senate hearing in the US Senate. It was a hearing called by then Senator Arlen Specter about embryonic stem cells and the promise of stem cell technology. And I was fortunate to be testifying with Christopher Reeve, who you know as a well-known actor, but who was also a very well-known victim of a horseback riding accident in which his neck was broken and he was paralyzed effectively from the neck down, and it led ultimately to his premature death. But Chris was always a big believer in what stem cells could do for human medicine, and he said a lot of things that are eminently quotable and thought-provoking. But one of the things that Chris said is summarized, is actually here, a direct quote. We are at a time when things that we used to think were impossible and unsolvable, we really don't say anymore. As a scientist, I've lost the ability to say something's impossible. It's amazing in the past 30 years how that's changed. And that in this particular case, we're actually getting closer to being able to use the kinds of materials I just talked about to really imagine that we will at some point, again, not a day, not a week, not a month, years, be able to really eliminate symptoms of disease and injury. It's a remarkable prospect, and I think we're living in a century where that will probably happen. So the question then is how to get there. So what I just laid out for you are a bunch of properties of these remarkable cells. In some ways, it's as though I listed all the properties of plastic that make it a really useful thing to build with, a really wonderful material. And so there are really three major kinds of issues that need to be dealt with in order to take the properties of stem cells and convert them into therapies that we can deliver to patients. And of course, at the end of the day, it's not just non-scientists and non-physicians who want us to move as quickly as possible. By the way, as a scientist, I have family members who have diseases too. And so we all share that goal of getting into experimental and then proven treatments as rapidly as possible. And I'll just lay out three of the issues that we currently tangle with. One has to do with the understanding of disease and how that can actually help us better develop therapies. A second has to do with unique types of safety issues we encounter with stem cells. And then the third has to do with the issues of communication and ensuring that patients are adequately protected when they choose to participate in experimental therapies. Okay, understanding disease. So there's a common sort of misconception that's quite understandable. And the common misconception is if you're dealing with a disease where cells are defective or where cells die, what you should do if you're going to use a cell replacement therapy using stem cells is to put 100% of your effort into replacing those cells that have died or are defective. That would be a very sensible way to think about it. Well, it turns out that there are important examples where, as a result of continued research on the medical problem, we've learned things that change how we might tackle the disease. And type 1 diabetes is a very good example of that, because as I told you at the beginning, type 1 diabetes is a disease where beta cells that make insulin and that live in the pancreas, those cells have died. Now, that might say to you, if I want to treat type 1 diabetes, I should make pancreatic beta cells from embryonic or reprogrammed stem cells, put them back into the person, and everything will be fine. And that would be incomplete. And the reason it's incomplete is there's a reason why the beta cells died in the diabetic to begin with. And it's because type 1 diabetes is almost certainly an autoimmune disease, where for reasons we don't understand, the immune system goes out of control and attacks the beta cells in the pancreas so that they die. And so if all you do is put new beta cells back into somebody who's got type 1 diabetes, the deranged immune system is still there and will attack the new beta cells. And so you have to somehow build a therapy or protection for those new beta cells that allows them to be protected from the immune system. So it's a case where having a deeper understanding of the disease is ultimately really important to thinking about how you're going to use stem cells to treat it. A second example of this comes from the disease ALS, amyotrophic lateral sclerosis, otherwise known as Lou Gehrig's disease. And this is another case where deeper study of the disorder has given us a better strategy with stem cells to try to treat these people. So let me remind you that ALS is a disease where a cell called a motor neuron dies for reasons we don't understand. Now, the motor neurons are cells that live ordinarily in the spinal cord, and they send out long projections from the spinal cord to the muscles in the periphery. And those projections are needed for the motor neurons to tell those muscles to contract, following signals from the brain. So there's a signal from the brain that says, okay, Larry, move your hand, and then the signal goes down my spinal cord, and then from the spinal cord out to the muscles in my fingers, voluntary movements. In ALS, those cells die, and as a result, patients with the disease ultimately become completely paralyzed because the cells that control voluntary movement, that control breathing, swallowing, and what have you, die, and that ultimately leads to the death of the patients. The typical time from diagnosis to death is on the order of 3 to 5 years, with some forms of the disease killing people in as little as a year or less following diagnosis. It's a dreadful disorder. There is only one FDA-approved drug to treat ALS. And that drug has no effect that the patient can perceive. It just increases the length of their life by a few months. So this is a tough problem. Now, you might expect that, or you might say, well, the way to treat ALS using stem cells would be to make new motor neurons to replace those that have died. That would be a sensible plan. But there are two problems with that plan ultimately. One, probably the most important problem, is that's going to be really difficult because of what you might think of as the wiring problem. If I'm going to take new motor neurons and transplant them into the spinal cord, they're going to have to regrow their connections out to the muscles in the periphery. It's the so-called wiring problem. That turns out to be a really difficult problem. Now, at some point, somebody will figure it out, hopefully sooner rather than later. But my personal view is I'm not going to hold my breath waiting for that problem to be solved. A more promising approach, in my opinion, developed as a result of 10 years of work from my lab here at UC San Diego and my colleague Don Cleveland's lab, also here at UC San Diego. Don is a longtime collaborator and friend. And what we learned from a great deal of work on mouse versions of ALS is that even though it is these motor neurons that are dying as a result of ALS, the surrounding cells in the spinal cord contribute in very important ways to the death of those motor neurons. And a particularly important type of cell that contributes are the so-called astrocytes. These are spinal cord cells whose normal job is, in a sense, to support the activities of the motor neurons, to clean up the trash, and to help supply them with valuable nutrients. And we have a great deal of evidence over the years that if you can replenish those astrocytes in animal versions of ALS, you can keep these motor neurons from dying as rapidly. Now, the good news about that realization is that the astrocytes are a kind of cell that's ultimately very easy to handle in the lab and surgically. They don't appear to need complicated wiring patterns, and in fact, they're somewhat migratory in the spinal cord. And so you could imagine if you could find a way to surgically transplant new astrocytes into the spinal cord of people with ALS, you might indeed be able to keep their motor neurons from dying. And so that's the project we've undertaken. We have a grant from the California Institute for Regenerative Medicine, which was established by Proposition 71 that Dilip told you about at the beginning. And this project is very simple to understand. In essence, we're taking human embryonic stem cells, and by appropriate growth and treatments, we generate large quantities of them. This is, by the way, a multi-institutional, multi-investigator collaboration. And then we generate cells that, following transplant, can generate astrocytes. And the hope is that in a human patient, those will rescue the motor neurons. That took me about 20 seconds to describe. If you go back into the early 60s, you'll recall that John Kennedy boldly walked to a blackboard one day. I'm being a little apocryphal here on literary license. And he drew a picture of the Earth, and he drew a picture of the moon, and he drew an arrow between them and said, we are going to go from the Earth to the moon and land a person safely on the moon. It took John Kennedy about 5 or 10 seconds to draw that little diagram, very easy to understand, and it took quite a bit of money and quite a bit of engineering prowess to pull that off. That's why when I say this is easy to understand, but it's going to take us more than a few minutes, a few weeks, or a few months to pull this off, it's because there is a great deal of engineering analogous to putting a person on the moon that it's going to take to figure out how to do this and do this properly. I'll give you a glimpse of that here. There are all sorts of intermediates we generate along the way. Every one of them has to be tested for safety, composition, the ability to potentially rescue the behavior in ALS animals. And of course, we have to do this because our first principle is once we get to testing these in people, we don't want to make those patients worse, right? That's a cardinal rule. And second, we want to have a reasonable expectation that the patients will improve. And so the good news is we're about 2 years through a 4-year project to do this. I'm very optimistic that we will get this into phase 1/2 clinical trials in 2 years or so. And that'll be a set of clinical trials to test safety and initial so-called efficacy, ability to rescue some of the symptoms of these people. There's no guarantee we'll be successful. This could fail for any of a number of reasons. There are other groups trying different sorts of approaches, but this illustrates for you one way we can go about trying to use these stem cells to try to develop an experimental therapy for a disease that we currently have absolutely no useful treatment for. Let me give you a second example where we're taking a very different sort of approach, and that's the case of Alzheimer's disease. So to remind you, Alzheimer's disease is incredibly common, unfortunately common. The estimates are as many as 10% of people over the age of 65, 50% of people over the age of 85 have this disorder. And of course, people who are my age, in their mid to late 50s, develop this disease as well. So Pat Summitt, the basketball coach at the University of Tennessee, very successful coach, recently had to retire because she developed Alzheimer's disease in her late 50s, an absolute tragedy. The disease is progressive, it's virtually incurable. We have no drugs that change the course of the disease. We hope that there are drugs in the pipeline, but there is no guarantee that the drugs in the pipeline will work or that they'll work on their own. It's a very tough problem. Now, part of the reason the problem has been tough is you have to ask the question, how would you go about inventing a therapy to treat Alzheimer's disease? because you need to understand something about the detailed biochemistry of what goes wrong in the brain cells to invent a drug, it turns out. The problem you have is, what are you going to do? So if you have an Alzheimer's patient, you can ask them questions and talk to them to figure out what their psychological profile and behavior is, what they remember, what they don't remember. There are tools like MRI and X-rays that let us look at low resolution and low sensitivity in their brains. And of course, we can study their brains after they've died of the disease. But the problem with studying their brains after they've died of the disease is that it's a little like studying the pattern of wreckage on the ground after a plane crash. So you can learn some things about why the plane crashed by studying the pattern of wreckage on the ground. But ultimately, what you really want to know is what was going on in the cockpit of the airplane before it began its unscheduled descent. You want to know, gee, were the pilots drunk? Were they playing with their laptops? Did one of them get locked in the bathroom? Or did the plane just run out of fuel or have some other mechanical problem? You're looking for the black box of the plane, which records those early events. And so with Alzheimer's disease, in a sense, what you're looking for is the black box of the disease, but we have no simple way to get that from people who are just at the very beginning of the disorder. I can't just take them back to the lab and drill a hole in their brain and take out a sample of material. I have to have some other approach. And it turns out that animal versions of Alzheimer's disease are not very good. They don't really develop true human Alzheimer's disease. We're back to the humans are not just big mice problem. So what we've been doing to try to test hypotheses and develop drugs is to take human embryonic stem cells or to reprogram skin cells from people who have Alzheimer's disease and then convert those into human brain cells in a dish. In essence, what we're trying to do is to generate in the lab human neurons that have Alzheimer's disease in the lab so that we can test ideas about what goes wrong and test drugs. And we've just launched a project with another CIRM grant in collaboration with the Sanford Burnham Institute down the road, where by taking advantage of the biochemical changes we've identified in human brain cells that have Alzheimer's disease in the lab, as a result of using this stem cell technology, we're starting a drug development project to try to develop a new class of drugs that may treat these biochemical changes. No guarantee we'll be successful again, but we think it's a very promising path forward and gives us a brand new window on how we might develop new agents to treat this terrible disease. So 2 final issues before I free you. First has to do with the issue of safety. As I said a few minutes ago, if we're going to treat diseases with novel experimental therapies, we better be sure as possible that we're not going to make people worse. And this little video clip summarizes the issue. You can see SpongeBob here has uncontrolled regeneration, and that ultimately can lead to, as we show here, bad outcomes. And of course, we want to avoid anything that even resembles this outcome if we use stem cell treatments for people with disease. But you know, the problem is that if you're going to treat people with stem cells, we have some very unique issues we're going to have to tangle with. You know, if you give somebody a drug and they have a bad reaction to it, you can stop giving them the drug. There's an exit strategy. Don't give them any more drug. But if you put cells in them, the problem is they are likely to hang around, you know? They might stay where you put them, they might not. They might go somewhere. And of course, you worry that if the cells do something unexpected, that could be bad. And that's not just a theoretical argument. This has been encountered over the years in a number of different clinical settings with treatments of Parkinson's disease by transplantation and by treatment of a number of other diseases using gene therapy or more recently different kinds of stem cell transplants. Now, that doesn't mean that you shouldn't go as rapidly as possible to develop these therapies. But you have to be very aware that when you use cells to treat disease, you're making a potentially permanent therapy in these people. And if there's a problem, you're going to have to deal with it. And so you want to have as much evidence for a safe intervention as you can before you start putting stem cells into people willy-nilly, if you will. The final issue really comes, in a sense, from these issues of safety I just mentioned, as well as from, I think, a behavior of humans that's as old as humanity, which is when something appears new and exciting, there's a charlatan or fraud down the block who will try to sell you an imitation product. And that has been happening in spades with stem cells. And in part, it's because of this problem. You know, as I just mentioned, it takes time to do things properly. These are engineering feats, ultimately. But of course, if you're a person with a disease, you're impatient. And it's easy for you to forget that if you're going to take a long journey, you got to start the first step and then the second step. But there are people who would take advantage of people being unwilling to be in it for the long haul. And believe me, if you have a disease that's going to kill a family member relatively rapidly, I can understand the impatience. On the other hand, the problem you bump into is illustrated here. There was a paper, and this is a case from the diabetes literature. There was a paper a few years ago in the Journal of the American Medical Association, a fairly prestigious journal, and I'll read you the title. Autologous non-myeloablative hematopoietic stem cell transplantation in newly diagnosed type 1 diabetes mellitus. A little bit of jargon. You know, guys like me love this sort of stuff. Okay, so that was the actual paper. And the paper reported a small clinical trial, only 10 or 20 patients. It was effectively a bone marrow transplantation to treat type 1 diabetes by trying to deal with the autoimmune aspect of the disease. Okay, great. And there were some good things in the paper, and there were some bad things in the paper. In the same issue of that journal, there was an editorial, perhaps somewhat breathless. Cellular therapy for type 1 diabetes, has the time come? A little bit optimistic for a small trial. We know that things that work in small numbers of people sometimes don't work as well in large numbers of people for statistical reasons. But literally within hours, in the London Times, diabetics cured in stem cell treatment advance. And literally within the next day or so, there were hundreds of entries in the comments and blog section. Diabetics wanting the treatment, people debating, did you need embryonic stem cells anymore? Did you need all sorts of things, wildly overblown interpretation. And this sort of thing has led to the growth of what I call the snake oil problem, or 60 Minutes calls the snake oil problem, where if you go to the web, you type in your least favorite disease, let's say, the disease you would like to have treated, and stem cell, you'll find dozens, if not hundreds of clinics around the world that will, for $10,000, $50,000, $100,000, sell you a stem cell therapy for that disease and claim that you will be treated, if not cured. In some cases, those clinics may not even be delivering cells. In some cases, we have no way of knowing, because if those clinics are outside of what we call a well-regulated environment, there's no accountability for what's in the vial that they necessarily inject into you. I mean, if you think about it, when you go to the drugstore and you're given a drug, how do you know that's what's in the bottle is what it's supposed to be? The answer is because the drug company says that's what's there, and there are big-time penalties if that's not true. People go to jail. But in poorly regulated environments, hey, anybody can say anything. And so that's led to the development of this horrible industry that has taken advantage of lots of people. Okay. A few closing thoughts. Thought number one. The problem of Alzheimer's disease in this country is a problem near and dear to my heart. And I think people forget just how desperate the situation is. If you go back to the 1950s, when polio was effectively an epidemic in the United States, until there was a credible vaccine available, and until it looked like a vaccine would be available, if you ask the question, well, what's the national plan for dealing with all of these victims of polio? The answer really was, we're going to build hotels and we're going to warehouse the people who are paralyzed and have to be on iron lungs. That was the plan until an effective vaccine in this case was developed. If you were to ask in 2012, what's the national plan for dealing with Alzheimer's disease? My interpretation of what I see in terms of how much we're spending to find a therapy or a cure is that our national plan is to build a lot of nursing homes to take care of people afflicted with this disease. And I guarantee you, as my generation starts hitting 65 and then 75, we are going to completely overwhelm the healthcare system. It's going to be a mess. Now, obviously, the way you find new therapies for a disease that you don't have therapies for is research. And people sometimes say, oh my God, research is so expensive. And of course, what Mary Lasker pointed out was, if you think research is expensive, try disease. And let me give you the numbers for Alzheimer's disease to illustrate for you just how true that is. So my estimate is that in last year, the United States probably spent something like $500 million on research to find a therapy for Alzheimer's disease. Sounds like a lot of money. The cost to the United States, both the public cost and the cost to all of us, both direct and indirect, unpaid care time, all the nasty costs when you lump them together, probably somewhere in the 400 to 500 billion range. About 1,000 times as much cost as what we're spending to find a therapy. Now, billions and millions, your average person has trouble really thinking about those very productively. So a nice analogy, I think, is imagine that as a family, you're spending $10,000 a year on a problem that you don't know how to solve. And you're only spending $10 a year to try to find a solution. That's the ratio we're talking about. I don't care what kind of deficit you're spending at. That's not enough, because that drip, drip, drip of 500 billion a year that's going to grow to $1 trillion pretty soon is vast compared to what we're spending to find an appropriate therapy. And by the way, if we find an appropriate therapy in the United States, we'll sell it to the rest of the world. That's good economic value. Okay, I'll finish again with Chris Reeve. Chris also said, at first when you dream about these things, they seem impossible. Then they become improbable. And of course, eventually we get to the point where they just seem inevitable. And we're at a point with stem cells where we're probably at the improbability stage. But in some areas, I think, as you can see, they're gradually turning into the inevitable. Thank you for your time.